So here's a linear second order constant coefficient non-homogeneous differential equation. If I was solving this the non-Laplace way, I'm going to solve it the Laplace way, but if I was solving it the non-Laplace way, I'd get the auxiliary equation, prime prime lambda squared, 1 prime, 1 lambda, 3y, so no prime, no lambda. I'd solve the auxiliary equation for the eigenvalues, 1 and 3. And so the homogeneous solution would be some constant, so c1 e to the t plus c2 e to the t. We see the eigenvalues here of 3 and 1. Then we'd have to add to the homogeneous solution, we'd have to add the particular solution. I would use unknown coefficients to get the particular solution. And so I would propose a particular solution of at plus b, a general line, because the target function is a line. I would figure out the a and b by subbing in y prime prime, which would be 0 in this case, and y prime, which would be a in this case, and y, which would be at plus b, and figure out what the a and the b have to be such that this particular solution solves the differential equation, hits the target function of t minus 2. Anyway, that's how I would do it. You would end up with a general solution that would be your homogeneous solution plus your particular solution. When you wrote it out like this, though, the a and the b would be known quantities because you would have found the a and the b using unknown coefficients. You would then find c1 and c2 using your initial conditions. Okay, that's how I would do it the eigenvalue auxiliary equation way. I'm going to use instead Laplace transforms. So from the chart I can see that, or from the chart, from a table, Laplace table, I can see that the transform of y prime prime is equal to s squared f minus sy naught minus s prime minus y prime naught, and y naught and y prime naught, we have numbers for those. So y naught is equal to 0. I would replace this with a 0, and y prime naught is equal to 1. I would replace that with a 1. Let's do that now. When I make y naught equal to 0, that makes this disappear. And when I make y prime naught equal to 1, there. And when I make y naught equal to 0, okay, I've absorbed the initial conditions into my transform. The transform of y prime is sf. On the table you would write sf minus y naught, but y naught is equal to 0, so I got rid of it. The transform of y is equal to f, so then the inverse transform of f is equal to y. From the table, the transform of t is 1 over s squared, and the transform of a constant is that constant over s, so 2 transforms to be 2 over s. These are all the transforms that I need. Here's the differential equation. I'm going to take the transform of the entire differential equation. So y prime prime, that's sf minus 1 with the initial conditions there, minus 4 times the transform of y prime is sf, plus 3 times the transform of y equals, now I have to transform the t minus 2, so the t transforms to be 1 over s squared, and the 2 transforms to be 2 over s. Now I'm in the Laplace world. My next step then is going to be solve this equation for f. So this piece has an f on it, this piece has an f on it, this piece has an f on it. It's only this minus 1 that doesn't have an f on it. So I'm going to bring that minus 1 over to the other side, so as a plus 1 over to the other side of the equation. And now all of these 3 pieces have an f, so I'm going to factor that f out. Oh, there's the auxiliary equation. That shows up, that's showing me that I'm doing the right thing. So auxiliary equation. I want to solve for f equals. Now it's probably a good idea for me to common denominator these pieces together, make it one rational function, and then divide out that bracket. So I would multiply, the common denominator is going to be s squared, so I would multiply top and bottom here by s squared, and this 1, I would write that 1 as s squared over s squared. And now when I put these together, they'll all be divided by the common denominator of s squared. There'll be a 1 minus 2s plus s squared. And I'll still have this f time. That's not f of, that's f multiplied by that bracket. And I guess I can, well, okay, now I can solve for f. So I'm going to divide both sides by that bracket. And now I have f equals. The next thing I want to do is, well, let's factor this. Let's write this in its factored form. I know that from when I saw it as the auxiliary equation, it was s minus 3 times s minus 1. So now it's in the factored form. And I want to do partial fractions on this piece. So I'm going to break this up into partial fractions. I'm going to ask the machine to do it, but you would just do this by hand. I say rather cavalierly. There's a lot of work to break that up into partial fractions. But I'm going to skip that part and just say, hey, give me partial fractions. So it did. So the step from here to here is do all that partial fraction stuff. So now I've got f equals, I'm going to clean this up a little bit so I can see. I'm going to write that as 2/9 times 1 over s minus 3. I'm going to write that as 2/9 times 1 over s. And I'm going to write that as 1/3 times 1 over s squared. So now I'm set to unLaplace. Notice if I take the Laplace of t, I get 1 over s squared. So when I take the inverse Laplace or unLaplace, that 1 over s squared is going to go back to t. When I transform a constant, I get a constant over s. So this 1 over s is going to go back to being 1. So 2/9 times 1 would just be the 2/9. This piece here, though, I don't have in my little chart that I made. But if I go back to the table, I will see that the transform of e to the at is equal to 1 over s minus a. So when I take the inverse transform of that, I should get e to the 3t. Now let's take the inverse transform of both sides. The transform of y becomes f, so the inverse transform of f becomes y. The transform of e to the at is 1 over s minus a, so if a was 3, that would be 1 over s minus 3. So when I take the inverse transform, that becomes e to the 3t. If I transform a number, I get a number over s, so inverse transform, that'll become 1. And when I transform t, I get 1 over s squared, so this will be t. And now, oh, there's my solution to the differential equation. When I take the inverse transform, it arrives and the c's are already there. Let's compare it to the answer that I thought I would get. I thought I would get some number times e to the t. I don't see that there. Oh, it's not there because it's some number times e to the t. It just so happens that first constant is 0. That's why I don't see it. Plus some number times e to the 3t. That's the homogeneous solution. The particular solution was supposed to be a line. Remember I had at plus b? There's the particular solution. There's the line. Now, we should check. I'm going to get rid of this 0t. There's how I would write the solution. A good check of this is supposed to go through the origin. When I make t equal to 0, I'm supposed to get y equals 0. When I make t equal to 0, I get 2/9 e to the 0 is 1. So 2/9, make that 0 so that piece disappears. So 2/9 minus 2/9 is 0. That checks out. It's also supposed to go through y prime equals 1. If I were to differentiate this, I would get, okay, the 2/9, the 3 comes down, that becomes 6/9 e to the 3t, plus the derivative here is just going to be a third, the derivative of a third t. And that's a constant, so when I differentiate, it disappears. Now let's make t equal to 0. E to the 0 is 1. I get 6/9. Oh yeah, 6/9 is 2/3. 2/3 plus 1/3, yeah, that's 1. So both initial conditions are satisfied, and I can see the proper pieces, the homogeneous solution and the particular solution.